Worked with Travis in the last few weeks. One of the things that I created for this conference... Alright, shut up! Talk starting. One of the things I created for this conference was an 8-stage puzzle hunt, very loosely based on some of the clues that have been in past MIT mystery hunts. The first 2 clues are embedded in the firmware of the badge. But I've seen very little uptake in the third and further rounds because I guess people just don't know it's there. The issue is that it's only in the B firmware of the badge, that's correct?
Yes.
If you look at your badge and if you look at the serial number NHB12, and you'll either have a B or you won't. If you have a B, dump the firmware over JTAG and you'll see the beginning of the work that I put in. So I think that's about it. If anyone has any questions, they're free to ask me at the end.
Cool. Where's Nick? Go get up here, neighbor. Nope. All right.
Oh. Go ahead. Oh, okay. Sorry about that. Good evening, everybody. Can you do a FinFitting demo?
Yeah, sure.
FinFitting? All right, this is my very good and neighborly friend, Travis Goodspeed, who is responsible for this awesome badge happening. So just for that, give him a round of applause. If there's anything wrong with it, I can guarantee you it's not Travis's fault.
It's Nick's fault.
It's my fault. Everything is my fault. And because of that, we're going to demonstrate something that we've been spreading at HackerCons all over the world. It's a new protocol. Well, not that new, but it's if you ever have an irreconcilable difference, something that you know you're never going to work out, with somebody who you should remain on neighborly terms with, you issue a fuck you packet like this. Fuck you, neighbor.
And then, to which there is a reply packet, a fuck you to neighbor packet. So suppose that Nick comes up to me and he says, Travis, my badge keeps turning off. What do? I tell him the battery, but there's still a little grudge left. So here's how we solve it.
Fuck you, neighbor.
Fuck you too, neighbor. And you shake hands, and the handshake is important. That's what ends the unneighborliness. It's all now over, and everything can be neighborly.
Neighborliness abounds, and we need a round of applause for that.
Right.
You ready to go? Yeah. So without any further ado, Travis Goodspeed, building and breaking the next Hope Badge. Huge round of applause this time. Woo!
Okay, so I could either give you a lecture about how the badge works here, which I assume you're all familiar with after the panel yesterday, and from walking around. So they run the OpenBeacon protocol, there's the website, and you can view the maps. The maps are now working. I could either do a second hour-long lecture on that, pissing off everyone else who worked in it because I'd be hogging the stage and all that stuff, or I could show you how to do something new with the badge. So in this talk, I'm barely going to mention OpenBeacon. I'm barely going to mention the Attendee Metadata project. Those are both very big, very complicated projects that do incredible things, but they are not the topic of this lecture. Instead, I'm going to tell you how to break into electronics like the Hope Badge. And one of these projects nearly got me sued. So neighborliness abounded in that, and that I did not. The idea is that in this lecture, I'm going to be telling you about 8 and 16-bit embedded systems and how to reverse engineer them. The computer inside your Hope Badge is about as powerful as a Sega Genesis. It might run a little bit faster, might run a little bit slower, bad at multiplication, better at power efficiency, but it is a computer. You can write a new program for it. You can flash that program into the badge. You can reverse engineer the code that's already there. And you can also start playing around with the radios. You can start broadcasting new messages, receiving messages, or you can start receiving messages that you're not supposed to, which, as we all know, is a lot of fun. So, let's see. The target hardware that we'll be talking about is the sort of stuff used in ZigBee, ANT, 802.15.4. This technology is also known as wireless sensor networks, or the smart grid. It's used in sports and medical equipment. The idea is that very often you want to broadcast a radio signal, but you don't want to waste a lot of power on it. And at the same time, you don't need to send a lot of data. You're not trying to stream video here. all you want to do is send a little chirp that says, "Here I am," as your badges do. So a quick show of hands. How many of you are very familiar with soldering? Awesome. How many of you know about the Intel 8051? Okay. How many of you are familiar with RISC assembly language, as opposed to x86, or anything non-x86? All right, cool. And how many of you understand the finer analog points of radio? Cool, because I don't. If you measure the antenna, I'm sure you've figured this out already. So this is the Next Hope badge, and I'm sure you've all got them. If you don't, security will escort you outside and be jerks and all of that fun stuff that they're paid to do. On this, let me grab a laser pointer. All right. So how many of you have taken a look at the design, grabbed the schematics off of SourceForge, and started to play around with your badge? Okay. For those of you who haven't, this chip here is the MSP430 microcontroller. Texas Instruments was kind enough to donate $25,000 worth of these to the conference. Let's give them a round. Their corporate web filter has also banned the conference website as a hacker website. So it goes. Over here, there's a Nordic RF radio chip. This is used in a variety of devices, one of which I'll go into a bit of detail about later. This radio speaks on any frequency from 2.400 gigahertz to 2.528 gigahertz. You just have a 7-bit field that describes the number of megahertz above 2.4 gigahertz that the channel is on. On the back, you can hack your badge with a badge hacking kit being sold by Mitch Altman and also by Lady Ada. This chip here is an FTDI USB to serial converter. It's the same thing that you have within an FTDI cable used for Arduinos. And then over on the edge, there is a USB plug. If your lights start flickering when you try to install this, it's because the power plug on the USB plug, that's the line furthest to the left, is mis-soldered. If it doesn't work at all, you've probably messed up some of these pins. It's not a soldering project for beginners, but if you do it, it's quite rewarding, and you get to do all sorts of fun stuff and fun neighborly stuff. This here is the CAD file design that was used for manufacturing the badge. All of this is in the SourceForge project. You can check it out by SVN. The project name is NH Badge. And later on, I assume this will be rolled into a distribution or something. But for now, grab SVN. That way, when I fix things, you can get the update immediately. Down here at the bottom, there is a general purpose I/O port. I don't mean to impose, but if someone could grab me a beer or a Club Mate, I would very much appreciate that. Yeah, so this general purpose I/O port is used as a touch sensor. If you hold the crystal on your board with one hand, thumb and forefinger, and then you also, with your other thumb and forefinger, touch along this row, you'll see the lights respond. You can get red, green, and blue. Green and blue cannot be lit at the same time. Green will take precedence. It's an electronic thing. Up here at the top is the JTAG port. This is what was used for commissioning the badges on the assembly line. This is also used for copying software out of the badge if perhaps there were some secrets here, such as the one that David was alluding to, that might or might not only be in the 12B model. Here we have an ICE port. This was broken out not because of any expectation that you would need it, but because it displays a neat little property, which is that you can wiretap the connection between the microcontroller and the radio. And I'll be talking about the details of that in a minute. But watching this connection, you can see exactly which channel the badge is running on, or exactly which packets it's sending out or receiving, exactly which MAC addresses it's listening on, which is, for this chip, a rather big deal. The only thing preventing you from sniffing all traffic is that the chip has no promiscuous mode. There is no way with this radio to sniff traffic aimed at every MAC address. You need to know at least the first 3 bytes. Up here is a BSL connector. This is used for connecting a bootloader, an FTDI cable for talking to the bootloader. It's sort of the poor man's way of doing the badge hacking kit on the back. I have not tested this, but I know that at least Mike Kershaw and perhaps others have it working. So this CAD file is enough to have boards manufactured. They were sent off to China. We got, they're panelized, and then there were these files that would come back to me. This is a machine translation, and a very poor one. Mike Zhao was our manufacturing contact in China, who was chosen by Mitch Altman, who was very neighborly. Mike took care of taking the Chinese that Google could not understand and translating it, and also making sure that this whole thing actually came out of the assembly line on time. A lot of that involved harassing me, for which I am terribly grateful. Otherwise, this would not have shipped on time. So this lecture will be in 3 parts. The first part will just simply show you how to sniff an SPI bus. The second part will describe how I reverse engineered another device which is compatible with the Hope badge. And then the third part will describe how to sniff and inject traffic from that device. And then if there's time at the end, I'll show you some neat little tricks that you can do. A big part of this lecture will be the GoodFET, which is an open source JTAG debugger. It's a project of mine. This is sort of an open source clone of both the proprietary Texas Instruments JTAG debugger, which I was very unhappy with in its Linux support at the time, and also the Hackaday Bus Pirate that Ian Lesnett made. This and the Bus Pirate don't share a code base. Maybe at some time they will, but for now it's best to have both devices. And it implements a lot of different protocols. So you can debug 8051 microcontrollers, the MSP430. We're about to commit to ARM support. You can read and write SPI and I2C EPROMs. You can talk through radios if you have a Nordic RF chip or any of the ChipCon devices. And I'll send you a board for free if you send a polite email and perhaps $5 by PayPal. The PayPal's optional. The people that do pay more than account for the people who don't. This is what a GoodFET looks like. You've got the FTDI chip on the left, the MSP430 in the middle, and the I/O ports on the right. If this looks similar to the Hope badge as far as the chip choices go, it's because they're almost identical. If you add the FTDI chip to your badge and also a USB plug, you can run the GoodFET firmware, which instead of beaconing out, as the default badge firmware does, just gives your computer access through Python to the radio. Having access to this radio, you can sniff and inject, you can jam. It's one command to hold a carrier wave on any given frequency with the Hope badge. First you need to figure out, before you can sniff something, which MAC address it's using, which frequency it's using. Otherwise, you're jumping around in a sea of noise. And as you're doing it with checksumming disabled, which is necessary when you don't yet know where the checksumming fields are, you wind up with a lot of packets that look kind of right but aren't. I had a thing at DEF CON in the Lost Mystery Challenge where I had a radio that was just spewing garbage whenever it wasn't near a transmitter. And I had this piping into Xterm. Xterm, when it receives garbage, does not crash, but it grabs strings from random areas of memory, a lot of which happen to be English or function names. So I kept thinking that I was getting legitimate traffic when I was actually getting further away from the transmitter. You need to watch out for confusing parts like this. In taking apart any radio, you've got to identify the antenna, the radio chip itself, the microcontroller. Sometimes these two are combined. They will be in the subject that comes later. In order to sniff the radio traffic, you have to identify where the serial port between them is. This is what's on the ICE connector on your badge. In this case, you just need to identify the radio chip, and then you look at the pin labels. In this case, we want the serial clock line, serial out, and serial input, and also ground. And they happen to all be in this nice little ring around the edge. So you identify these signals, and then having found them on the board, you can figure out exactly where to tap on the board as a whole. I like to use hypodermic syringes for these. A kind thanks to Eric Michaud for getting me my beer. I appreciate it. Yes. I'm sure this beer will cost me in court later. All right, so you pick your tapping point, which would be here, and then you shove syringes into the board, or you can get very high gauge wire wrap wire, which can be fed through the vias that are only intended to move the copper from one side of the board to the other. You can slip a wire in there, tap it on with a bit of solder, and get a clean connection. On an oscilloscope, this is what the clock line looks like. Here you have 2 bytes being transferred. There's a little pause in between them. The clock is idling low, and then the